Okay, let's get started. So we're going to continue emerging memory technologies, and then we'll talk about flash memory, which was an emerging memory technology about 30 years ago. And you know that it's everywhere in our lives today. And it's going to be fun, I think, to see that emerging memory technology looking backward a little bit. Now we are looking forward. If you remember, an architect's role is looking everywhere. You have eyes everywhere. Now we're looking forward to emerging memory technologies to enable them. And also looking down on the technology and figuring out what's coming next and enabling it also. And then we're going to look backward into the flash memory and see what are how it became enabled, and also what are the things that go into existing flash controllers to make it work today. Okay, that's going to be a long lecture actually, but we're not going to have enough time to cover everything. Okay, so this is where we left off. We were talking about other opportunities with emerging technologies, if you remember. And we talked a lot about merging of memory and storage. We didn't talk about applications, but applications is very interesting, right? It's sometimes very hard to imagine applications before the technology is there. Now that flash memory is there, it's enabled a lot of different things today. I mean, this is an application that I think flash memory is enabled, really. Or maybe a system design, you call it. Maybe it's not a single application, it's many, many applications, right? That wasn't there before. So if we were closed-minded, like some people in the world, then this wouldn't have been enabled, perhaps. You could argue this is not necessarily a good thing, but any technology is not a good thing or a bad thing. It's a technology. It depends on what you do with it, right? So that's the importance of looking forward, basically. You need to enable the technology because you don't know what it will bring after the technology comes and becomes successful, or becomes mildly successful, and then someone wants to make it successful going into the future, or figures out an application that takes advantage of it. So I like talking about this mindset, but this mindset is critical going forward because I think there is a lot of, there's always this tension between people who want to move the needle to the next step and people who want to stay back and don't do anything. And you need to be very careful in that tension, because if you stay back and do nothing, then things may not improve at all. Right? Okay, so we were not going to talk about this thing, but what we're going to talk about right now is kind of related to this robust system design, and then we're going to be done with emerging memory technologies for now. Even though it's a much larger topic, we don't have enough time to do a lot more. So this is what we were talking about. If you actually have a very fast non-volatile memory device, now this is very close to the technology we have for the volatile memory, which is DRAM, in terms of performance, latency, maybe much better energy in some aspects. So why don't we actually unify memory and storage management in a single unit, such that we get rid of the software management overhead that we normally have with file systems? And we talked about this. I gave you some performance numbers. This improves energy and performance, and I didn't talk about this, but this could potentially simplify the programming model as well. We're going to talk about programming a little bit more right now. Okay, so basically, can we make main memory persistent and take advantage of it at the application level? Certainly there are a lot of interesting application studies that could be done here, which we're not going to talk about, but if you're really interested, I'd be happy to give you pointers. People are trying to, for example, port databases completely into persistent memory, key value stores, whatever you may want to think of. Okay, and this is something that I showed you. Basically, this is one potential programming model. You may have persistent objects. Today, we don't expose persistence to arrays. Whenever you declare an array in C or any language, it's volatile, right? You don't expect that value to persist after a power loss, for example, even after you update it. That's not how it works. You go through the file system interface. But if you actually have a persistent array declared, that's a completely different model. And now you actually need to make sure that this works correctly, even if you have a power loss. But that's the power of having very fast non-volatile memory. You can have this persistent object, and your program may be more robust as a result. Okay, and we discussed some of the issues related to this. Of course, we didn't solve all of the problems because this is an emerging technology, and there's a lot more to do in this area. And I pointed you to this paper, which we're not going to cover in more detail, but this is actually a forward-looking paper that discusses a lot of issues related to persistent memory. And I'm proud of this paper for not only that reason, but also because we were able to get Intel and AMD on the same paper together, collaborating with them. Not many papers are like that. Okay, so the big challenge and opportunity is combined memory and storage, as we've discussed, and can we actually unify the interfaces to all data? And this is where we left off actually. One key challenge, there are many key challenges, but I'm going to focus on one of them that's interesting because there needs to be a lot of system support potentially for this. How do you ensure the consistency of a system or data if all of the data that you have in the memory is persistent? So there are two extremes of this. I'll give you, I briefly introduced the problem basically. Whenever you get a power loss, for example, and if you're running a program that is written for non-persistent memory and that gets magically executed on persistent memory, it crashes. Now you need to restart the program. And it's already updated the persistent memory, so when it restarts, the data values that you have in persistent memory are basically whatever it was updated before. First of all, how do you restart the program? And how do you ensure that it gets correct result at the end when it's restarted? So this is something that you need to enable for transitioning between volatile memories to persistent memories. And there are multiple approaches. One approach would be to say, don't put any burden to the programmer. System magically handles these programs. Even though they are not written with persistent memory in mind, system is going to execute them correctly. This is one extreme approach, of course. Now the system needs to do a lot of work to make sure that whenever a program, let's say, crashes, or you have a power failure, or whatever reason the program basically in the middle stops, and you restart it, it still gets the correct result, even though persistent memory may be updated in between. Make sense? Okay, the second is, of course, the exact opposite. The system doesn't do anything. Well, that may be hard, but system at least provides some support maybe, but let the programmer handle it. The programmer should be writing programs that whenever they crash, they should not be producing incorrect results if they get restarted, for example. And of course, the programmer now needs to program with particular mechanisms or libraries where one example that I gave last time was transactional semantics. If you're modifying some persistent data, maybe you actually use transactions to modify that data. We'll talk about that briefly, but I'm not going to go into detail. There's some literature, and this is also an evolving area right now as to how you should program persistent memory. I'm going to briefly talk about part of this approach, and then we're going to develop a technique that's more programmer transparent. I think the right answer is somewhere in the middle, because there are many alternatives in between. You'll see that this technique is actually very heavy on the system, and this technique is probably very heavy on the programmer, and you may not be able to transition easily to persistent memory if you expect all of your programs to be rewritten completely, right? Okay, so let's look at the problem first. Basically, this is also called the crash consistency problem. It's not a new problem, it's a relatively old problem. Storage systems actually need to handle this. But let's assume that you need to add a node to a linked list. What you need to do is link this node to the next and link to the previous. And if you have a crash in between, you may get an inconsistent state before both of the links happen, basically. That's not good, of course. And if you have persistent memory, the link that you updated may persist actually. Okay, so this could be one example when a crash happens, depending on how you write the program. You may not be linked to the rest of the linked list, for example. Okay, so a system crash can result in inconsistent memory state. So how do current solutions handle this? So people actually have proposed explicit interfaces to manage this sort of consistency in persistent memory. These are some examples. Basically, this is what you do. Whenever you want to have multiple persistent updates to persist together, you do some sort of transaction. And you could argue there are different ways of doing it. I'm not going to go into the details, but this is one example. You insert a new node, and it's an atomic, it's all or none execution. Meaning that if you get a system crash before this atomic block completely executes, you have to start from the beginning. So you need to keep enough state in the program or in the system somehow to go back to the beginning of this atomic block. If you don't get a system crash while this is executing, basically you go to the end and then you commit all the results over here. That's the idea. This is actually used for concurrency also, and actually problems are similar between concurrency and as well as persistent, but there are differences also, but I'm not going to go into that in detail. So hopefully you understand that this is one way of solving the problem. This of course requires support from the programmer. The programmer needs to write these atomic blocks. They should first figure out where they should insert these atomic blocks. They should be very careful because the system can crash at any point, right? And you have persistent updates that you've done to memory. You need to make sure that none of that is inconsistent. Okay, so the problem is, and there needs to be some system support to support these atomic blocks, of course, which I'm not going to again talk about. If you're really interested, you can take a look at some of these papers, although none of them really in detail discuss the detailed implementation. But one thing is clear: if you have to go back and change every program such that it has these constructs, you'll limit the adoption of a new technology like non-volatile memory. You have to rewrite the code with clear partition between volatile and non-volatile data in this case. Because whenever you're manipulating persistent data, you need to at least think about whether or not you need something like this. So it's a burden on the programmers. So let's, an example code is if you want to update a node in a persistent hash table, this is one example. This is without any persistency. Basically, this is volatile. Let's take a look at how do we actually convert it such that you make it similar to what we've discussed. Basically, I'll go over here because I don't have enough space there to actually see the code. But basically, you need to create a new function, and you need to be declare things to be persistent. For example, this is a persistent hash table, and you need to update this function such that it's more persistent. Yeah, so you need to manually declare things. Maybe you need a new implementation for this get chain because you may actually crash in the middle, and if you updated some pointers in between, again, too bad you have the same problem that we've just discussed. And maybe this is a third-party code. Now, if third-party code, the library that somebody has written, doesn't have any understanding of persistent memory, it was written for volatile memory, what do you do in that case, right? How do you ensure that that works? That's actually not an easy thing. If you have third-party libraries that are not written to assume that the memory is persistent, you can run into the exact same problem that I just discussed, and you don't know about it even. So you need to be very careful, and you need to use libraries that are there for persistency, if you will. This is similar to actually multi-threading, right? If you have multi-threading, and if you're calling a library, and the library is not thread safe, meaning that it's not aware of this multi-threading, then you have a problem. Better not call it. Right? You need to find thread safe libraries. It's very similar to that, except this is really about updating the data and persistent storage. Okay, and then you may actually have a prohibited operation because you may not be directly able you may not want to directly modify persistent memory. You may actually have a backup, store the old data. So if you're actually doing a transactional model, for example, you don't want to directly update a location. You want to update that location only if you know the entire function completes. Right? So how do you actually ensure that? It could be the programmer's burden to do that. That way you need to actually have a buffer where you buffer things until you know that, okay, this is going to complete, and then flush that buffer. And but managing that buffer is actually important because you may get a crash in the middle of flushing that buffer. That's why I think having system support for that is very important. Okay, so clearly there's a burden on the programmers whenever you want to go and modify even a simple hash table update code like this to become persistent. And if you're really interested, you can read the paper that I'm going to reference later on. So I'll give you one approach that we've been looking at. Our approach actually has been the other extreme. The extreme is, okay, programmer does nothing. Let's try to design a system where the system handles everything, hardware, software, cooperative, such that whenever you crash in the middle of a program, you can go back to that point and restart the program and still get correct result. And so clearly we're going to employ some checkpointing. So it's software transparent consistency in persistent memory systems. So key idea is very simple. You periodically checkpoint state and you recover to a previous checkpoint on crash. So how do you do that is actually very, very hairy. This has been also proposed for fault tolerance, but persistent memory has its own idiosyncrasies. People actually do some of this checkpointing in large-scale, high-performance computing systems, for example. But again, they don't deal with the persistent memory issues. They always assume that storage system handles the persistency nicely. So whenever a program crashes, storage system is consistent already to begin with. So that's the difference here. Here, we're not assuming storage system magically ensures that it's consistent because the storage system is really main memory right now, and you may have updated some data in main memory. Whereas if you're actually executing a program, let's say in an HPC system, and if you updated memory, it's all volatile updates. You haven't touched storage. So you can go back to a much more earlier state that's consistent in terms of storage and a clean state where you can restart your program. Okay. So I'll give you the summary and then we'll go into a little bit more detail, but I'd encourage you to read the paper because I won't be able to go into a whole lot of detail. This is not an easy thing to do actually. This is very hairy. Even if you have a single node, it's very hairy. And actually I know that several people, like Fusion.io, before they got bought by SanDisk, they actually were looking at very similar solutions and they didn't have as much hardware support as we had, so their overheads were very large. But then unfortunately they got bought, so it's not clear if their products are really fully state-of-the-art at this point. Okay, so basically it's a new hardware-based checkpointing mechanism. The idea is to checkpoint at multiple granularities to reduce both checkpointing latency and metadata overhead. We'll talk about what's required in checkpointing. There's always a trade-off between how long it takes to checkpoint, how long it takes to recover, and how much metadata do you need to keep around. Because if you checkpoint not so often, what happens is you need to go back to a previous checkpoint if something happens in between. But if you don't checkpoint not very often, that means that you need to buffer a lot of data somewhere. So there's always a trade-off between metadata overhead as well as data overhead and checkpointing latency. And also, this is really critical whenever you're designing a system, either for fault tolerance, well, this is also fault tolerance, but in a different way. Whenever you're designing a system that's checkpointing, you don't want to checkpoint, execute. You want to overlap those latencies, otherwise it's too much overhead. And you'll see that this will adapt to DRAM and non-volatile memory characteristics. Some things are easier in DRAM. DRAM is fast, so this is going to take advantage of hybrid memory. It's not going to be just non-volatile memory. Because if you want to really build a very high performance system, you have to have DRAM in the system, assuming that your persistent non-volatile memory is similar to PCM in terms of its characteristics. That's what we're going to assume. And you'll see that this is actually, in the end, the system that's designed performs within, let's say, 5% of an idealized DRAM with zero cost consistency. Idealized DRAM is a DRAM that's magically persistent memory, a memory with the characteristics of DRAM, but also persistence. Okay, and the source code is available, so if you really want to advance the state of the art, the source code is out there. It may not be very easy to read, but that's always the case actually with, in general, any source code. So let me talk about this in a little bit more detail. So I've already given you this basically crash consistency problem. I'm going to skip this a little bit. System crash can result in inconsistent memory state. So the current solutions, we've already gone through that also. So basically our goal was multiple over here. First of all, executing legacy applications. If your memory magically becomes persistent overnight, your legacy applications will break. You won't be able to execute them because of the problem that we've discussed, right? Because they're written to, actually, there's always an implicit assumption that whenever you update memory, it's volatile, right? Actually, your operating systems assume that also. Whenever you update memory, it's volatile. This is actually very much ingrained in how we program today. The assumption is that, yeah, exactly. When we crash, the memory goes away, right? Only the files remain. But if your memory becomes persistent, now that assumption is completely broken. As a result, your legacy applications, I can guarantee you that pretty much all of them will break, including the operating systems. Actually, a really interesting research direction is looking into operating system or virtual or hypervisor designs that adapt to persistent memory fully. If all of your memory is persistent, how does the design of the operating system and hypervisor and virtual machines change? Amazingly, not many systems researchers are looking into this, because there's also this interesting thing in systems research. If this thing doesn't exist, a lot of software people are scared of touching it. This is actually the subject of real architecture research. People should be doing this research in architecture. If this thing doesn't exist, architects are very good at, oh, okay, let me take a look into it and make it work. That mindset is very interesting, actually. Whereas if the mindset, there's also another divide between software and hardware. A lot of people are in the software space and they basically say, oh, this thing doesn't exist, so I don't care. So it's good to have this hardware-software cooperative mindset where you actually think, oh, okay, this thing is very interesting, so how do I redesign my software if it exists 10 years later? And that's exactly what forward-looking companies would be doing. Yes?
Just to understand the problem as like today, the occasional computer crashes, and it restarts, it just assume there's garbage in the memory and starts like this, so how is it now different?
It just assumes what?
Like, if I remember correctly, my project starts, it must assume that there can be any value in the memory. And so it needs to initialize it. So how does it change if the memory is suddenly persistent? It doesn't really change.
So if you completely restart the program from the beginning, maybe.
You mean?
But we want to start it somewhere in between, right? Yeah. And also, I'm not sure if that's true for operating systems. If operating systems may update some structures.
Okay.
Yeah. Anyway, we can talk about that in detail. But if you completely restart from the beginning, and if you reinitialize everything, that could be true. Yeah. Okay, but we don't want to do that. That's a lot of waste, right? Okay. Okay, so the next thing is reducing burden on the programmers. So clearly, you don't want programmers to be programming with rewriting all of the code and hopefully enable easier integration on NVM. Okay, so basically we don't want any modification in the code and things to work very efficiently. So how do you get that? We want exactly this to work. If you get a crash somewhere, maybe you restart from somewhere in between. I don't know where exactly. We'll talk about that checkpointing. There's always a trade-off between where you restart and how much performance you lose. Okay, so we've already talked about that. So the approach is periodic checkpointing of data that's managed by hardware. So this is one way of doing it, right? So you normally divide the program into epochs where your program runs and you checkpoint for a while after it runs. And you could do this. But as I said, that's not a good approach because you're wasting a lot of time on checkpointing. And okay, if you crash somewhere over here, let's say, you go back to the end of the checkpoint and then you restart execution. So clearly, if you checkpoint often, whenever you crash, you lose little work. But then the problem is your checkpointing overhead is always exposed to the program. But it is transparent to the application and system. So how can we make it more efficient? We're going to talk about that. So basically, whenever you're running, you have a working location, and whenever you're checkpointing, you checkpoint it to some other location. So hopefully this is clear. You need to have 2 copies of data if you have checkpointing. You can designate one as working location and the other as checkpoint location. And whenever you checkpoint, you copy one to the other, and then you keep the running so that you can recover back to the checkpoint location without updating that checkpoint location while you're running. That's the idea. The problem is this huge checkpointing latency. Like after you're finished the running, you need to checkpoint the data, and that takes a long time. So how do you actually, so let's take a look at this one. So basically, the metadata that you need to keep is affected by the checkpointing granularity. You could checkpoint at the page granularity. Then you need to keep track of the metadata at the page level. This is very similar to what we've discussed in terms of designing a large DRAM cache, right? What is the metadata or tag store that you need to keep track of the things that are checkpointed? You could do it at the page granularity, which is a large granularity. Or you could do it, in this case, you need to have 1 entry per page. Your metadata is small. That's good. Or you could do it at the cache block granularity. This is smaller. You have 1 entry per block, and this is huge metadata. So there's a trade-off over here. But checkpointing latency actually makes a difference. So okay, the idea, I'm going through the ideas relatively quickly, but if you want to checkpoint at the page granularity, that may actually be slow, right? Especially if you want to write it to persistent memory. That's how you checkpoint actually. You need to write the data into persistent memory to checkpoint. And if you do it at a huge page granularity always, that takes a lot of time. But writing to the persistent memory at a small granularity actually takes a short time. So this affects your latency as well. It doesn't only affect your metadata, but it affects your latency. But they go against each other, as you can see. Here, the metadata overhead is large, but latency is low. Here, the metadata overhead is small, but the latency is large. So how do you take that into account? So let's take a look at latency and location. So if you want to write back data from the DRAM to NVM, because you buffer the data in DRAM, and you want to checkpoint it now to NVM, you need to update the metadata table. And there's a long latency of writing back data to NVM. So if you do DRAM, a page-based write back, it takes long, which is what I said. Or you could do NVM-based remapping. So basically, you just update the metadata. There's no copying of data. and you write the data in a new location, basically. So let's say, basically, if you have a lot of good locality of page in DRAM, maybe you keep that page in DRAM, and after it's fully updated, you write it back to NVM in a streaming manner. So that actually reduces your latency. That's one of the ideas that we're going to explore. But it does have some long latency, but if you actually have good spatial locality, as we discussed last time, streaming accesses to NVM is not bad. Now the downside is, of course, these are writes, they're not reads. As a result, you need to actually still pay some penalty. So it's very hard to get rid of the penalty of writing to NVM because it takes a long time to write, as we've discussed, right? But if you want to checkpoint, you'll have to do that. But if you actually don't have good locality, if you have, let's say, your accesses are to a single block, let's say, maybe you don't need to put the data into DRAM. That's another choice that we can discuss separately. But you can simply write the data, copy the data from one location NVM to this other location NVM and update the metadata. This is called NVM-based remapping. This way you can actually copy the data from one part of NVM to another part of NVM, and this part may be designated as the checkpoint or the new location, and one of the other ones is designated as a checkpoint. Okay, so basically we have a trade-off between granularity. If you want small granularity, you have large metadata. If you want large granularity, you have small metadata. And you have a latency trade-off and location trade-off also. If you actually want to write back from DRAM, it takes long latency, even if you want to write a single block. But if you want to remap in NVM, it's actually short latency because you can actually change the pointer also to a different location or just do a single write. And you may actually accelerate this with other mechanisms that we've discussed, like row clone, that we're not going to go into. Okay, so basically there are two mechanisms over here. One is dual granularity checkpointing, adapt the checkpointing to the memory type because of this. And the second is, as I already said, overlap the execution and checkpointing. Let's take a look at the first one. So these are the mechanisms that are proposed. These are not necessarily the only mechanisms. That's why I'm going through this relatively fast. But if you have a good locality, high write locality, keep those pages in DRAM such that you expose, as we discussed earlier, you do the writes in DRAM and those writes don't get exposed to the NVM. And also you collect these updated large page inside the DRAM. If you have low locality, keep that in NVM. And since you don't have a lot of locality, then you're not going to actually lose a lot of performance, perhaps. So this is basically good for streaming writes, if you're streaming through a 4 kilobyte page and writing to every block. And this is good for random writes. Although you could make a case for random writes over here as well, right? There's no question about that. If you have good locality over here in a single block, you may want to actually keep it in DRAM. I'm actually right now giving you two extremes. Here you don't have good locality, you're just doing one write, and you don't have a lot of locality in that cache block. So it's good to keep it over here. Okay, so that's the gist of the idea, but of course there are a lot more details when you want to make it as high performance, so you actually need to go into more detail. As you see, this is one trade-off space. This is the checkpoint granularity, small versus large, cache block versus page, and this is the location of the working copy. It could be in DRAM, and when you write to it, you need to checkpoint it in NVM, so you need to do write back. It could be in NVM, and then you need to actually do remapping of the data. But as you can see, there are cases where things are inefficient. You may not want to be there. And there are cases where things are partially efficient. And there's no case where things are extremely efficient. So that's how you need to deal with checkpointing. I'm not going to go into the detail. You read the paper for more detail. Let's go into the second one. The second one is a lot more intuitive, of course, because this applies to any system, right? Not a hybrid memory. This is what you want to do. You don't want to do this. You want to do this for high performance. Meaning that while you're checkpointing, you start the next epoch. Now this doesn't come for free, obviously, because here you needed to have a checkpointed copy and a working copy. And then when you're transitioning from here to here, you update the checkpointed copy with the working copy over here. Right? That's the idea. But here, you really need to have 3 copies of the same data that you updated. Basically, you may actually have a working copy here, and then that's being checkpointed. You need to have another working copy that doesn't actually update either of those. So you need to have at least 3 copies for this to work. Of course, this also hides the latency of checkpointing. So if you have a long write back from DRAM to NVM, this may be okay because you started operating on the other data, other copy. Okay, does that make sense? I've gone through this at high level, but if you want to go into the details, it's very nasty. Because you need to make it work in a real system, and that's where you read the paper and work on the code. Okay, so actually dealing with 3 copies makes it more nasty than it should be, I think. Okay, so let's take a look at the evaluation. So this is what is proposed. If you really want to do it purely in hardware, you need to have a lot of support in your memory controller. Basically, your memory controller needs to be aware of what is the working copy, what is the checkpointed copy, what is being checkpointed, meaning that it needs to do a lot of address translation. It gets an address, and that is something that needs to be updated, and the memory controller knows which epoch the system is in at this point, and it redirects the address to the correct place. And of course, it needs to also ensure that the checkpoint is done correctly. And this is an example of the memory address space. Basically, there are multiple regions over here. There's a backup region. There's a working region. In this case, we use DRAM, but there's no reason why it cannot be partitioned between DRAM and NVM. This is the design trade-off we made. We wanted to work on DRAM only, and then put the data in NVM. We wanted to minimize writes. And then there's a checkpoint region, and there's another checkpoint region to ensure that you actually can handle 3 copies at the same time. So this is the processor's view, because we're not changing the program, right? The processor sees the same thing, but the memory controller internally does something completely different to ensure that this checkpointing is done without any problems. And you don't worry about this. I mean, you can read the paper if you're interested. So basically, how do you after all of this is done, you need to verify that it's correct, and then we simulate. I'll give you some key results very quickly. Basically, these are the comparison points. We had an ideal system. We assume that it's DRAM based completely, and it has magically persistent. There is no cost for consistency, and this is the lowest latency system clearly. And we had an ideal NVM based system. Again, it has no cost for consistency, but NVM has higher latency than DRAM, similar to what we assumed for PCM, for example. And there are other systems, a journaling based system, for example. It's kind of a hybrid. It commits dirty cache blocks, and it leverages DRAM to buffer these dirty blocks. So here you actually need to modify the software. The software does journaling itself to ensure that it can recover to a consistent state. And the last one is, again, it does shadow paging. Again, this is a software-based solution. It's kind of like a hybrid solution. It uses both DRAM and NVM. But basically, it does a lot of copy on write. It has shadow pages. So essentially, the software itself manages these different copies of pages to ensure that whenever you crash, you have a consistent state, and you separate this working copy from the checkpointed copy. If you're interested, I mean, these are very well-known approaches actually to program consistent systems, and you can take a look at the paper for more detail. But the key is basically you need to leverage DRAM to buffer blocks, otherwise your performance is not very high. So here we actually really cared about the performance of the system. Okay, so let's take a look at some examples of this. I'm not going to go through this in detail again, but this is, actually I don't even know what application this was. Basically these are 2 applications that we constructed, random access versus sequential access. If you look at the random access, it turns out its journaling is actually much better than shadow paging. Because shadow paging actually keeps things at the page granularity, and it's good if you have spatial locality. Whereas if you don't have spatial locality, that page granularity is very expensive. You need to do page copies all the time. This is actually a perfect application that row clone can accelerate actually, because you have copy on write, a lot of copy on writes. So if you don't have good spatial locality, journaling is much better. So its execution time is low, basically. This is traffic to non-volatile memory. And ThionVM actually adapts to it. ThionVM automatically does this. There's no explicit journaling or shadow paging. So automatically, the memory controller uses this DRAM-based write back, and as a result, its traffic to non-volatile memory is relatively low because it's buffering the entire page inside DRAM. Right? Similar to, well, not in this case, actually. This is the case where it's buffering the entire page in DRAM because it's sequential. It has good spatial locality. But in this case, it's using you have more random access, so you actually do the remapping inside the non-volatile memory. So the traffic is very low over here. So you get essentially you get the best of both worlds. In this case, you get performance close to journaling, which is good for random access. In this case, you have sequential accesses, which means that if you actually do the writes in a full page and then do the copy after that, it's good because you're keeping an entire page over here. Whereas if you kept journaling at a smaller granularity, you have more writes to non-volatile memory. So shadow paging is much better over here, and the INVM, as you can see, is close enough. Maybe it's not as close as we want, but it's not that bad also. Okay, but it's done automatically. Here, the programmer puts a lot of effort to do shadow paging. The programmer puts a lot of effort to do journaling. Automatically, we get almost the best of both worlds by adapting to the access patterns. Okay, this is overlapping of checkpointing and execution. So if you actually do that, then basically this is the execution time. That was traffic to non-volatile memory. This is the execution time. By overlapping checkpointing and execution, you actually perform better than journaling and shadow paging. Because journaling and shadow paging, the programmer needs to do that. I guess they could potentially overlap checkpointing and execution, but it's not that easy. They need to actually really put a lot of effort into their code. Maybe one thread is doing journaling, one thread is doing shadow paging, and you need to adapt. That's not easy. Whereas in this system, it's automatically happening in parallel, right? As a result, the execution time of the INVM is better than the software-based versions in both cases. Yeah. Okay. So basically, what this means is only this % of the execution time is stalled because of checkpointing. The rest of the execution time is not exposed. So you're checkpointing, but that is not exposed to the system. Okay. Okay, so this is the performance of legacy code. You magically port your code. Well, you don't port your code, basically. This is the same code, and your persistent memory becomes persistent. And if you had an ideal DRAM, that's your performance. If you had an ideal NVM, you would lose some performance, which is not that bad, actually, for these applications at least. And with INVM, you get very close to an idealized DRAM. And actually, you're better than the NVM-based system because we're utilizing the DRAM in this case. Basically, the key takeaway is by designing the system such that it can do this automatic checkpointing while adapting to the access patterns such that you keep the access patterns that are more suitable for different memories. In those different memories, you can provide consistency with low performance overhead. And if you're actually really interested in more studies, this is an example for key value stores, for example. And these are different ways of writing the key value store using journaling and shadow paging. And you see that I think the takeaway is very similar. The transaction throughput of the key value store is with the mechanism that we have is very close to the ideal DRAM-based system. Okay, so basically conclusion, this is one extreme, as I said. It's an extreme way of providing support without assuming anything from the programmer to have a hardware-based checkpointing mechanism. It checkpoints at multiple granularities to minimize both latency and metadata overhead. It overlaps checkpointing and execution. And it adapts to DRAM and NVM characteristics. If you have spatial locality in writes, keep it in DRAM and then checkpoint at that large granularity into NVM. If you have random access, right, keep it in NVM and then do the checkpointing by changing the pointer to the different copies. And the hope is that this sort of mechanisms or system support can enable widespread adoption of persistent memory. And if you're really interested, there's a lot of actually interesting work to be done in this area, and I would suggest you take a look at this paper as well as the source code. Okay, now that I've described this, let me give you my opinion. So there are two extremes, as I said, right? Programmer-based, you punt on the programmer, and programmer handles everything to make sure their code works when you have persistent memory, of course in exploiting high performance. Or you say, okay, the programmer doesn't do anything and the system does everything. It's good to explore both directions for sure. Of course, I think the programmer-based direction is easier to explore because if you punt on the programmer, you can explore that a lot more easily. The system-based direction is a bit harder to explore because there's a lot of nitty-gritty that you need to deal with. Whenever you restart the system, it needs to work completely correctly, right? You cannot basically cut any corners here. Whereas programmer, you can always say, okay, the entire program is a transaction. Well, that's not probably good. Actually, that's but at least you can actually play with the granularity. But here you could also play with the granularity. But once you play with the granularity, your overheads increase a lot also. So I think the real place is somewhere in between. Basically, system needs to provide some support for persistence, and the programmer needs to do something. But you meet in the middle somewhere, and as a result, you're much more efficient than either of them can provide alone. But I don't know where that middle place is actually. That middle place is not researched very well in literature, so we'll see if people find out that middle place. But I know that the extreme solution that we have is very hairy. It's very difficult to get right, especially if you have a large-scale system. Okay, any questions? I've talked about this more than I wanted to, but I think this is a very interesting and important topic. No questions? Okay, so this gives you one example of how you might want to both optimize the system and provide support for software. But there's actually a lot more that's needed, I think. And one of the examples is how do you actually help the programmers to exploit this persistence. It's not also easy. Because right now, what happens is you write to files, and you may actually modify a lot of data that you may not really need. But if your memory is persistent at the byte level, every byte is important. So how do you actually help the programmers to automatically rewrite their programs? And we've done some work in this actually. This is actually a tool that can help programmers to identify, oh, these are the parts that you should maybe look at such that you might want to make these persistent and make these not persistent. I'd suggest you take a look at it. I'm not going to go into detail, but there's a lot of need for such tools where the programmers, actually it's not easy to figure out exactly what you should make persistent, what you should not make persistent. Of course, you can make everything persistent and rely on the transactions like we've discussed, or rely on the system support. But there's a lot of overhead for that persistent because you're writing to memory and you need to ensure that things work correctly with crash consistency. So if you can separate your data such that what needs to be persistent is actually stored and marked nicely compared to the other things, then that's good. But the problem is with the file system mindset, it's a totally different mindset. You're not really directly modifying memory. So you really need to help the programmers to move from that file system mindset to actually to the memory mindset. And if you don't know what I say, try to convert your file system-based program to a persistent memory-based program, and you will know what I say, I think. Okay, so I think I'm going to conclude the emerging memory technologies with this. It's going to be very similar to processing in memory. Basically, the future of emerging memory technologies is bright, I think. There are a lot of challenges in the technology we've discussed, as well as the applications and problems and requirements, right? But if we can actually overcome those challenges, this can enable orders of magnitude improvements, and I've given you some orders of magnitude, and it can also enable new applications and computing systems. But again, this is another problem that requires thinking across the stack, and it requires us to design enabling systems. Because a lot of the things that we've described so far, actually, there's nothing that's at a single level, really. You need to do multiple things at the software-hardware interface, as well as at different layers. So this is, if you remember, I use the exact same slide for processing in memory also. And I use this slide also in processing in memory. If you're in doubt about emerging technologies, refer to flash memory, right? This was actually a very doubtful emerging technology for at least 2 decades. But it has emerged, and we're going to actually talk a lot more about this paper in a little bit. It has emerged, but it emerged with a lot of effort that people put into it. And a lot of people believing in it and making it happen, a lot of people disbelieving it. And also for financial interest, they may want to disbelieve it, right? Because they may have vested interest in some other technology. And that also happens, actually. If you want to put a product out, if you're an entrepreneur, you need to be very careful in terms of how you deal with the competitors. But this is a technology that's an example. That's why I think it's very fitting that we continue with the flash memory lecture after this. Any questions? I don't want to start the flash memory lecture without taking a break, I think. This may not be a bad place to take a break. Okay, let's start after 15 minutes.